Yeah, hi everyone. I have a great pleasure to introduce Karl Pierce from Flatiron Institute with his talk about ITers and software library advancements.
Perfect. Thank you. Thank you for inviting me. Yeah, so I'm here from the Flatiron Institute to talk about our ITensor software. I'm going to focus more on the backend development, so I'm going to speed through a couple of the intro portions. So if anyone has any questions about this, feel free to ask me after the talk. So I'm going to talk about ITensor, which is now a more massive library, which was inspired by tensor diagrams. So I'll talk about in a second what this means to do tensor algorithms. And so we can kind of think about the library as this multi-level thing. So ITensor itself sits in the middle, is in some small wrapper around two big things on the top and bottom. So the top is a user-facing portion of ITensor, which is any graph or tensor algorithm library. So something that does DMRG in quantum physics or graph algorithms or whatever you might think of to use tensors for. And then on the below ITensors is this ND-tensors library. And so that's what I'm going to focus on here. This is the meat of what ITensors is. And so this ND-tensor has lots of functionality and it's growing. And the goal of it is to be some kind of plug and play place to do optimization. So one is it has informed indices, and so this is kind of what makes ITensor, and I'll go over this in the next slide. So it's got information about blocking patterns, physics metadata, also what is an index, like how big it is, etc. There are different data types that are possible. So if you're going to use GPU array, CPU array, any other kind of contrived data type you might want to use. There's also different floating point precision, backends. We support different data patterns, so you might want to have block data or sparse data or represent blocks as SVDs or anything kind of thing. And then in the future, we're looking towards doing memory and task managers using things like cuTensor or offload MPI. And as I said, it's this plug-and-play library. So now we're working on building about robust backend extensions. So far we support things like GPUs, this CUDA.jl libraries, most of the GPUs. I'm writing jail arrays. And then in the future, we want to support things like tensor operations and Dagger. And so you can do this memory managers, or you can easily switch out what you're doing when you're doing the tensor algorithms. So just as a really quick refresher, as you might not know what a tensor is, so a tensor is an n-dimensional array, and so we have a tensor here, as I said, the diagrams, and this is the tensor diagram. So tensors are represented as these vertices on a graph, and then the lines coming out to the edges from a vertice tell you how many orders or how big, what's the dimensionality of the data. So here we have one leg, so it's an order 1 tensor. 2 legs is an order 2 tensor, makes a matrix, and then 3 legs and higher makes any higher order tensor. And this graph representation is really nice because we can do things like represent a sum, which maybe looks a little messy when you're just staring at it, as some graph. And you can tell here really easily that the leg connecting M and T is A, and this means in this representation that we sum over the leg A. So we can use this to build graph algorithms. And this is kind of where ITensors shines. And so ITensors was originally created for this unique indexing system, which removes ambiguity from your algorithms. You don't have to write sums, which I'll show in a second. And it helps you quickly construct tensor network algorithms. We can easily build some kind of big tensor network. So just as a quick, before I show how to build a tensor network, I want to show you how to build a tensor. So here we have we're going to build 2 tensors, A and B. Right now they have no legs. They're just nothing. We can assign legs to them by first creating these indices I've talked about. So here we make an index I that has the length 2. And the inside and ITensors, we have information about the dimension, like how big that leg is, and some unique ID. And so we can build many legs. Sorry, just jumped ahead. We can build many legs, and all of them will have their own unique ID number. You can see here, they all have different numbers. And now we have 4 legs. So that we have legs, and we have tensors, but we need to put them together. So we can easily put them together by doing something like ITensor of ij. So now A has the legs ij, and B has the legs kjl. So it looks like this. And then from here, we can do something easy like build a really trivial tensor network by just contracting A and B. And in our diagram, now we take the J legs together and stick them together. Now, in conventional syntax, you might do something like create a for loop, and then you're going to loop over ijkl, and you have to write your things like this, and J for A lives in the second position, and for B lives in the first position, and you really are, you get the same numbers, right? But the problem with this conventional notation, or syntax, is that if you accidentally switch J and I, they both have the same dimension, so this code runs perfectly fine, but now all your numbers are broken. You get wrong numbers. So ITensors make sure that this doesn't happen by using this unique indexing. It indexes the legs by this ID number, and when we do some kind of tensor operation like contract, we look at the legs and say, okay, these are the same, we're going to contract over these and stick them together. So that you can't accidentally switch I and J. You just call star and it does it for you. And now we can throw the letters back. And so what we've been working on in ITensors is to create robust and flexible implementations in this ND-tensors library. We're trying to make it more and more easy to change everything about it and still be able to rapidly construct tensor algorithms and have relatively high efficiency. So we want things like CPU and GPU accessibility, still have this complex data patterns like sparsity, but we also want it to be memory and time efficient. So as an example, I'm going to show constructing this tensor network and then converting it to GPU. So here we want to construct this tensor network and create it as some function f. So we can do this by making some legs. So these are all dense legs. So these are just legs that describe the extent of a tensor. And then I form the tensors A, B, C, and D like this. And we just easily make this function like I showed before by multiplying A times B times C times D. And now we have this tensor network exactly constructed using ITensors. And let's say we want to take the gradient of this network with respect to B. We can just grab the zygote and then take the gradient with respect to the second variable, which is B. So now we have this new tensor diagram where B is gone because we took the derivative with respect to B. And as I said, we want to put this on GPU. So what we're going to do is we are going to add CUDA and then use the cuAdapt function. And now everything is on GPU. And it all works. So that's great. But how do you do it with maybe some more complex structure? Like we want to do some kind of block sparse tensor structure based on physics. So this can be done too. So we're going to build this network now, and the directional arrows come from some physical description. So we're going to encode this physical description in the index type here. So that's based on some quantum number or what have you, whatever kind of information you want to give this tensor. This describes the leg sizes. So now this has two blocks of size 1. And we can construct the tensor network again very easily. Now we just need to include these daggers, which describe our physics of the problem. We can construct this network exactly by doing this. And then we can still take the gradient of it. So this is all on CPU. This is what we could do before, and we want to convert it to GPU. So we're going to add CUDA and then call the cuAdapt function. And now everything's on GPU, and it works exactly as you would expect, except on GPU. So you ask, but is it performant? So just to show you, I did some square tensor contractions on a CPU on my workstation, which is like 32 cores. I think it's in like a Ice Lake or something like this. 32 threads, I mean. And then I did it on a GPU, which is this RTX A6000, both with float 64 precision. And as you see, as you go from smaller to bigger contractions, you get a bigger speed up with GPU. So this is great, right? We can use GPUs and we can do contractions, but tensor algorithms are more complicated than contractions alone. So then we ask the question, well, what would it take to make efficient GPU code with this tensor network algorithm? So tensor network algorithms, that seems a little bit maybe ethereal. So maybe I'll walk through one just to show what kind of operations we might need to do. So if we have, let's say we're going to do DMRG algorithm, it takes an n-dimensional function, this psi here, and represents it as products of lower dimensional tensors. So this goes from an n-dimensional tensor to many order 2 and 3 tensors. And the goal of this algorithm is to find the best tensors x1, x2, x3, x4, etc. And there's some prescribed method to do this. We can just create some variational problem. We can take the gradient of this variational problem. We can contract all the tensors to get some kind of problem that we're going to then take a truncated SVD, plug it back into the beginning, and redo this loop over and over and over again until it stops doing anything interesting. So that's all of the physics here. We're going to do this. We want to do this, but on a GPU. But the number of operations can be complicated. And where the complicatedness comes from is actually the generic coding backend of our code and Julia. So we want to be able to do things like just give our tensors to some functions that describe maybe are based on, say, abstract array versus GPU array, so that our code works out well. But we found some problems. And so one problem was when we were like investigating types in dealing with wrapped arrays. So if we make some matrix here, and I have a function f on the left-hand side, which just says what is the type of our matrix. So here, if I just have a regular matrix, I give it to f, it says, hello, I'm an abstract array. We all expect that. Say I use the CUDA adapt function, and now I have an abstract GPU array. But if I add some kind of wrapping to this, we can have issues where, my wrapper kind of loses information about the type that I had before. And so this is bad for us in our code. This can cause failure and cause you to call some Julia base implemented code that is very, very slow or has scalar indexing problems. And so we wanted some way to be able to capture our types as they move down some pipe and move them and put them in the correct pipe so that they do the right thing. And so we created this internal module called expose. And it's very simple. It's just a small struct that has two types in the parameters, an unwrapped type and the original object type. So we just call this unwrap array type function, which I'm not going to describe here, to uncover deep down what our actual type is, and when we keep the original type information here. This is similar to other packages like simple traits, where traits, trait wrappers. It's just, again, based on trait dispatching we're trying to do. And we can use this to make specific code, so we can make now functions that are dependent on this expose struct, and we can have generic expose struct, so everything can run through, and we can just specifically catch the cases which are failing for some reason. So here we're going to catch cases that if they were wrapped, but deep down they're actually an abstract GPU array, I'm going to give it to this second function. Say I'm an exposed GPU, and I'm a GPU exposed instead of the generic exposed. So if we do this again with our code from before, and instead of giving just A, I give expose of A, I get what I would expect from a normal matrix. I'm going to use the GPU, the CUDA version. I get what I would expect from the GPU array. And if I go to trying to wrap it on some arbitrary amount of wrappers, I always get the right behavior. I'm going to go into the GPU exposed and then give an abstract array, give an abstract GPU array. So this is nice, and this functionality allows us to write a lot of code that maybe isn't flowing down the right pipes, and it allows us to fix it. But one thing we found was now we have to create a function unwrap array type. So we need to have some maybe basis of investigating types to determine if it has some other parent type, so that if it's wrapped. What we found when we started looking at the type parameters, that type parameters are kind of a wild land. Anyone can do anything they want with them. So I'll demonstrate this here. So you can have a matrix. And if we look at the type of the matrix, it's exactly what we expect. It's an array with float 64, which maybe describes the L type, and 2, which describes something like the ndim. We have functions to call back and get those numbers. All right, so if we think about maybe abstract array types are going to have an L type and then an ndim always. So what does the type of the transpose look like? Well, okay. Transpose is some wrapper, and it has L type, but now it has the parent type, the matrix of float 64, and it doesn't have ndim information exactly in the type parameters, but we can ascertain that by moving down into the wrapped type. So maybe for wrapped types, we're going to say that the first is the L type and the second is the parent. Well, if we just make a view of something, we don't see that. We see now it has L type, endims, the parent type, which I can again ascertain the endims from now, and then other information that is thrown in there, like information about what the ranges of the view look like. Okay, so now we don't really, it's all over the place. And so if I graph coup, I see again, it looks like an abstract array, but now it has this other thing that they're using, which is some information about the device memory, which is really important information. All of this is very important information. We want to be able to probe this and also maybe have an understanding for our library of where to find information about things to help standardize the process. So we made an internal package called type parameters accessor in our modules. And both of these two packages, we're working to make them just publicly available. There are just portions of our code right now, but we're working to make them standalone packages. And so in this, we can do very easy thing to begin with. We can say we're going to use this struct called position, which just helps us keep us type stable. And we're going to use it to get type parameters of a type, which is not very exciting, right? We're going to make a matrix type, and we're going to say, give me the type parameter of the second position. And very excitingly, it tells you to. So, okay. But we can do this for any arbitrary type, so you don't need to know anything about the type. You can just say, okay, tell me the third position of this type. If it's there, it will tell you this is what it is. If it doesn't have a third position, it will fail and say, this type doesn't have a third position. Why are you asking for that? So that's all fine, but we wanted to push this. We wanted to do other things. We want to know about, be able to like somehow register where parent types live for certain wrappers, maybe. And this code is very similar to the accessor's code. So a different thing we wanted to do was maybe if we have a type, be able to set positions of the type. So this is something you can easily do since we're already looking at the type. Maybe we can easily just make a new type and replace the position n with a new name. So we can do this like make matrix type again, and we can set the type parameter of the first position. Very easy, and this is exciting. It gives us matrix float 64, but in a type stable way. So I'm not going to show that here, but we worked hard to make sure this was as type stable as we could with using some Julia internals. The other thing we were interested in doing was saying, like, if we're converting from one type to another, we might have some information, let's say going from an array to a coup array, but not all the information. So we might want to specify. So if the type information is there, set it, but if it's if the type information is there, don't set it, but if it isn't there, set it in. So that's complicated to say, but if we're going to specify the type parameter of a matrix, the L type, the first position, it has no type information specified in that position, so now we have matrix float 64. But if we were to try to specify the type parameter of M, which already says float 32, this does nothing and just returns float 32. So it can be helpful in like converting from one type to another where you maybe have more information or less information on one type than the other type. The third thing, which I think is really exciting, is that we can name positions in our types. So here, this is our registering that we do. So we can register the names of each position with an associative function. So here, for an array, I've already told you the first position is an L type, right? And we can look at that and say, okay, that's L type. We know that. But the computer doesn't know it, and Julia doesn't know it. So now we can register it with our type parameter system and say, when I tell you set the type parameter of L type, that's position 1 for array, and that's position n for something else. And then the second one is endims. So then we can also say set the endims of a transpose, and that won't do anything, right? Because we're not going to register that, and we'll throw an error. So as I said, we can say, okay, now set the L type of a matrix to float 64. We get matrix float 64. We can also put this into specify, so specify the type parameter of array, the endims to 2, and now it gives us matrix. And we can also do multiple at a time. So you can say, you just have to go from type parameter to type parameters with an S, and then you can give a tuple for each like L type and endims, but I won't show that here. But okay, ltype and ndim are both registered function names that are for base Julia. But what we can do is we can actually just make our own functions that kind of rely on type parameter accessors. So let's say I call the third position of an abstract GPU array. Let's say I want to determine maybe some memory information about an abstract GPU array. So I might have a function called storage mode. So this will tell me for maybe for a Q array if it's on device memory or unified memory. And I'm going to use type parameter to say, give me the type parameter of this array type at the storage mode position, wherever that is for the class I've registered. So in general, this isn't set, and we'll just say, hey, you haven't registered the function storage mode with this type. But if we do something like, say, tell type parameters, well, the position of the storage mode for Q array is position 3, then we can do something like set the type parameter of the storage mode to device memory of a Q matrix, and now we have the Q matrix over here. So we can kind of use this as some ad hoc method to name type parameter positions of a type. But we want to take it one step further, and we wanted to also use this as a system to create default parameters. So often in our code, we were finding we're running through the code, we would change the type from 64 to 32, and things would fail because we have accidentally hard-coded in defaults, like to float 64. So in this method, if we just rely on specifying or setting the types using this set default parameter or default parameters, then we can just have one place where our defaults are explicitly defined and then used throughout our whole package. So here we're going to define the default type parameters for array as a vector of float 64. So then I can say, well, set the default parameter for this matrix of L type, and we'll plug in float 64. Or I can just say, set the default parameters, here's an array, go for it, and it will tell me, okay, vector float 64. So this has been very helpful. So these two tools together allow us to reach down into type information and unpack things and then have our code piped in the right direction. And so now with all of this tooling, we can run computations on tensor algorithms on GPU and CPU and move towards more generic coding in general. So don't worry too much. This is just setting up some problem. And when you're looking at these graphs, from left to right, the problem goes from easy to hard. So there's more computations needed on the right side than the left side. And you see as you need more computations, the GPU, these two, get more, have a more of an advantage over the CPU code, which is exactly what we hoped for and expected. And we didn't really change the DMRG algorithm. We just made sure everything was using the correct library functions using this dispatch. So this is for dense. So this assumes everything is a dense matrix. There's no block sparsity. But we also want to be able to use it for our more complicated storage structures. So we also have it now working for the block sparse, but block sparse is kind of hard to quantify because sparsity could be anything. Right? So dense is one case, but I'm just here to show you a couple block sparse results. So we have maybe some small number, not too many blocks, and they're all relatively big. The black is 0, and the white is some numbers. So we're going to use to compute DMRG, and this is a matrix in a matrix contraction in the DMRG algorithm. So this is what our data structure kind of looks like in general. And you can see, because we have relatively big blocks, and these blocks will get bigger as the problem goes from left to right, we see bigger advantage using the block sparse GPU code compared to the block sparse CPU code. But it all works. But at the end of the day, it's not a free lunch and with GPUs, and we still break down for problems that we're working on. So if we go to some other kind of sparsity pattern, so we have lots of very tiny blocks in our problem, and some really high structure to make it so that analyzing the block structure is more expensive than actually doing the contractions, then we see that GPUs are losing. So this blue line is our CPU code, and the other lines are our GPU code, and GPU is always more expensive no matter how hard we make the problem, just because the problem is so logically dependent compared to numeric contraction dependent. So this kind of lends us to learn more about our program and learn more of what we need to plug into the back end of ITensors. So what we're working on next is more advanced block tensor algorithms. So we're adding more types of symmetry. We're also letting blocks be different kinds of blocks. So we're thinking about blocks as maybe of a tree structure, the tensor is a tree, or blocks could be something like a hierarchical decomposition, so they're SVDs. The last slide shows that we need something like memory managers and buffers and tasks manager support so that we can load all of the tasks onto the GPU we need to do and not worry so much about doing this logic. That makes it expensive on GPU, and we can get performance there. So we're working with NVIDIA's team for their cuTensor. And just as a side project, all of this code uses mutable data, so you can go in and touch it, but we're thinking about using some kind of immutable data. Maybe your elements are some value of a function, or you want to have lazy zeros as blocks, things like that. We're also working on that front. And so thank you for your time. This is all I have to say.
Any questions?
Yeah, thank you for the very nice talk. My question is, how does ITensor compare with other tensor-based frameworks that are available in the Julia community? The one that comes to mind is one that I used in a package of mine called one more einsum.jl.
Yeah, so I'm not sure how performant they are compared to each other. I can tell you that when I am doing performance computations of things like GEM, that we're reaching towards the peak performance of the machine. So if everyone is doing everything with BLOS and you don't have many transposes, then the best you can get is as good as your computer is, and we should both be the same. But then it depends on, are you doing high dimensional tensors? So you have order 5 tensor where you have to do a lot of transposes. So I'm not really sure. I think that's a very packed question. But I think one thing where we're interested in beating them or thinking about going beyond is that we have this smart indexing system. So one thing is, so I have tensor operations up, right? And there's some kind of einsum-like formation. So the thought is that these kind of libraries could be some backend that you plug into ITensor, right? So ITensor really is this smart index system. And whatever we use for actually doing the graph analysis and then contracting doesn't have to be what we wrote. So right now, we have some handwritten algorithms that do transposes, but these easily could be ported off to somewhere else. So if we're using something like Dagger, and Dagger has a D array, and the D array has its own implementation of permutations and contractions, they're going to deal with that. And that's what we're also working with cuTensor to do, because right now we're doing all these transposes for this really small block portion, and we're losing significantly when we go to GPU. But we should be able to see much better performance than we're getting. So it's not that I'm trying to beat them. I'm trying to make a flexible system. So if you say, oh, this is working really well for me, you can just say, okay, I'm going to be using your einsum program, and all of the code that would be running through my code is going to be switched over to that code. Yeah.
Any more questions?
When you do the DMRG on the GPU, is
Yeah.
it also doing like the SVDs on the GPU
Yes.
too? It's all
Yes. Yeah. So right now, because we don't have any really good way internally in ITensors to do memory management and task management, say to have the tasks start on a CPU and give things to GPU, we have no way to do simultaneous CPU and GPU tasking. So if your tensors live on GPU and you say, give me an SVD on GPU, it will most likely do it on GPU. That being said, if your GPU doesn't have SVDs, it won't do it. So if you're doing metal and metals don't have SVD, you can't do SVD on your GPU because it just will fail. It will give you an internal compiler error in metal. So for the most part, in this code that I showed, every operation you see for all of the algorithms is being run on GPU, all of the logic, everything.
Do you think if you were able to split those tasks up?
So this is also dependent on how big your SVD is, right? So if my SVD is relatively small and my contractions are relatively big, then even if SVD is 10 times slower than it should be, I'm going to lose more trying to communicate it to CPU and backwards. And that's where something like, again, that task manager like star PU, Dagger, and distribute, anyone who is task managing and thinking about load balancing is going to be able to answer that better. This code is, we're not specifically trying to write that thing, we're trying to write code so that you can use whatever you want to do that thing.
Thanks.
But you'd also have to maybe internally to DMRG write your own distribution, like maybe use MPI or something like that.
Then I would like to ask one question from me. So, kind of to put in a mental map, it's kind of like PyTorch named tensors, no?
Similar to PyTorch tensors?
Named tensors.
Oh, yes.
Yeah.
Yeah, I would say yes. Yeah. And so we're switching, really what's happening is that we're completely rewriting the internals of ND tensor to be, it's going to be changed from an ND tensor to a named array. It's exactly that. It's like a named tensor, and then you can build a graph based on that. Then you can run graph algorithms on the names. Yeah.
Yeah, it was really great and really cool advancements of ITensor software in Julia. So round of applause for our speaker.